Hi, welcome to Competitive Cracker. I hope you all are preparing well for the upcoming CSIR examination. In order to help you for that preparation, we have come up with a new video. In this video, we will be discussing about the electric field due to a thin rod. Okay, so this comes under the electrodynamics, and here it comes in the continuous charge distribution. It is not a point charge distribution that you all know. So here we will be discussing about three aspects. The first one is the symmetric. At a symmetric point, we will be finding out the electric field due to the thin rod at a symmetric point, and then we will be discussing about the electric field due to a thin rod at an asymmetric point, and then we will generalize this by discussing about the electric field which is generated by a thin rod at an arbitrary point, at any point. Clear? So let us discuss. So I welcome you all to this video once again, and let us discuss about that. So what is this thin rod? Thin rod. See here, this is my thin rod. See, this is my thin rod, which is of length L, and which is having a charge density lambda. So first we are going to discuss about here we are discussing about the electric field due to a point which is symmetric to this thin rod at a symmetric point. At a symmetric point. At a symmetric point. Is it clear? So let us discuss. See, this is my thin rod, and this is my point. That means it is exactly at the center, which is a symmetric. And here I have to find the electric field. What is the electric field? So this point is at a distance Z, and this length is L by 2, and this length is also L by 2. Okay. So here we have to find the electric field. So since this point is symmetric to both sides, I have to take two elements. This element is having a charge dq. This element is also having a charge dq. Okay. So this element is at a distance x. This element is also at a distance x. So clear? So this is for total of length L. This is my system. To find the electric field at this point, I have to put a +1 coulomb charge here. So when I place a +1 coulomb charge, I have to find whether it is attracted or repelled by each element. See, this is my first element, suppose, and this is my second element. Okay. So due to one, the +1 coulomb will be attracted or repelled. It will be repelled by, because both are like charges, because it is having plus lambda. It is having plus lambda charge distribution. It is having plus lambda charge density on this rod. So it is repelled. Clear? So that is DE1. Clear? And then due to this this +1 coulomb will be attracted or repelled. This will be again be repelled. So this is DE2. Clear? So these two vectors, this is theta, this is also theta, because this is x and this is z. So these both angles will be same. So we can resolve this DE1 and DE2. We can resolve this. So this DE1 could be resolved like this. Since this is theta, this is also theta, and this is a DE1 cos theta, and this is a DE1 sin theta. Clear? And I can resolve this dE2 like this. So this is a dE2 sine theta, and this is a dE2 cos theta. dE2 cos theta. Clear? So when you see this, you can write dE. What is dE? dE is k, which is 1 by 4 pi epsilon 0 into dQ divided by this distance. What is this distance? This is under root x square plus z square. When you square that, it will be x square plus z square. K dQ divided by x square plus z square. Clear? So you can see that dE1 will be equal to dE2. dE1 is equal to dE2. Why? Because all are same. So from this we can conclude that dE1 equals dE2. dE1 equals dE2. Clear? So when you since dE1 is equal to dE2, dE2 sine theta and dE1 sine theta cancels each other. Why? Because they are opposite to each other. They are opposite. They are equal and they are opposite vectors. Okay, so they cancel each other. So the total electric field could be written as dE equals 2dE cos theta. 2dE cos theta. What is this? Substitute for dE, 2k dQ divided by x square plus z square into cos theta. What is cos theta there? It is z divided by x square plus z square whole power 1 by 2. Clear? So what is this dE? dE is equal to 2kz into dQ divided by x square plus z square whole power 3 by 2. So you got dE is equal to 2kz dQ divided by x square plus z square whole power 3 by 2. What is our next step? We have to find the total electric field. So in order to find the total electric field, what is this? We have lambda. What is lambda? It is linear charge density. That is dQ by dx. So dQ is equal to lambda dx. dQ is equal to lambda dx. So we got dE equals 2kz dQ divided by x square plus z square whole power 3 by 2. Next, substitute for this dQ. What is d? We have lambda. What is lambda? Lambda is linear charge density. Linear charge density. Lambda equals dQ by dx. Lambda is dQ by dx. Therefore, dQ is equal to lambda dx. dQ equals lambda dx. So substitute it here. So therefore, dE equals 2kz into lambda dx divided by x square plus z square whole power 3 by 2. So I got the value of dE. Correct? So in order to find the value of electric field, I have to just integrate this integrate this small value dE. Isn't it? So what is it? Take out the constants. 2k z lambda. All these are constants. Then integral dx divided by x square plus z square whole power 3 by 2. Understood? So what is it? Electric field is equal to 2kz lambda into what is the value of this integral? What is the limits? What are the limits of this integral? 0 to L by 2. The limits of this integral are from 0 to L by 2. Clear? So limits are from 0 to L by 2. So what is the value of this integral? This is x by z square into x square plus z square whole power 1 by 2. From where to where? 0 to L by 2. 0 to L by 2. Just substitute the limits. It is equal to 2k z into lambda into this is substitute for x. It is L by 2 divided by, I'm taking out this z square, so into z square plus L square by 4, z square plus L square by 4. Clear? So z and z square cancels. So this is L by 2, and if you take the LCM, it is a 4z square plus L square by 4. That by 4, when it comes outside the root, it will be 2, and that 2 and this 2 will cancel, and we will get electric field as E is equal to 2k lambda by z, 2k lambda by z into 2k lambda by z into L by 4z square, L by 4z square plus L square whole power 1 by 2. So you got the electric field as 2k lambda by z into L by 4z square plus L square whole power 1 by 2. Is it clear? So if you need, you can further substitute for lambda L. This lambda L is nothing but total charge Q. You can substitute it there. So electric field E is equal to, this is one expression, it is right. So it is lambda into L is Q, so it is 2kq by Z into 4Z square plus L square whole power 1 by 2. So this is another expression. Just substitute lambda L is equal to Q, and you will get 2kq divided by Z into 4Z square plus L square whole power 1 by 2. Is it clear? So this is how we find out the electric field due to a thin rod at a symmetric point. At a symmetric point which is at a distance Z from the rod. So you got 2k lambda by Z into L by 4Z square plus L square whole power 1 by 2, or just lambda L is equal to Q, and just substitute that, and 2kq divided by Z into 4Z square plus L square whole power 1 by 2. Is it clear? So next, this is not the general case. So next we are going to see the second case. The point is towards the end. The point is towards the end of the rod. The point is towards the end of the rod. That means like this. See, this is my rod and the point is towards the end. This is my point, and here I have to find the electric field at a distance Z, and the length of the rod is L. Okay, so see, this is my rod. So this is my rod, and this is my point. This is my point at a distance Z. And see, in order to find the electric field at this point, I have to take a single element. I have to take a single element of charge dq and width dx, which is at a distance x from the point. X from the point. Okay. So due to this, I have to find the electric field. If I place a plus 1 coulomb, whether it will be attracted or repelled, it will be repelled. So it will be repelled. This is the electric field. Okay, so that small electric field. Since this is theta, you can resolve this into two components. This can be resolved into two components. So this is a dE sine theta, and this is a dE cos theta. dE sine theta and dE cos theta. Clear? So if you write the total electric field dE, which is equal to dE sine theta in the I cap direction plus dE cos theta in the j cap direction. Clear? So just substitute for dE. What is dE here? dE is equal to this is x, this is z. So k k 1 by 4 pi epsilon 0 into dq divided by x square plus z square, right? This is dE. Just substitute it here. So k dq divided by x square plus z square into, what is sine theta there? This is x by x square plus z square whole power 1 by 2 in I cap direction, plus k dq divided by x square plus z square into, what is cos theta? It is z by x square plus z square whole power 1 by 2 in j cap direction. Understood? So this is equal to k into dq into x divided by x square plus z square whole power 3 by 2 I cap, plus k z into dq divided by x square plus z square whole power 3 by 2 in j cap direction. As we did in the previous case, lambda is equal to dq by dx and dq is equal to lambda dx. Substitute it here. So this is equal to k lambda into x dx divided by x square plus z square whole power 3 by 2 I cap, plus k lambda into z dx divided by x square plus z square whole power 3 by 2 in j cap direction. I hope it is clear. Next, we have to find the total electric field. Total electric field is equal to, integral dE. Integral dE from where to where? From 0 to L. Clear? So that is, if you take the constants outside, it will be k lambda into integral from 0 to L x dx divided by x square plus z square whole power 3 by 2 in I cap direction, plus k lambda into z integral 0 to L dx divided by the x square plus z square whole power 3 by 2 in j cap direction. Hope it is clear. So electric field is equal to k lambda into what is the value? X dx, integral x dx divided by x square plus z square whole power 3 by 2. What is the value? It is minus 1 by x square plus z square whole power 1 by 2. From where to where? 0 to L, plus k lambda z into this is x divided by z square into x square plus z square whole power 1 by 2 in j cap direction. Is it clear? So I hope you know this, the value of these special integrals. So very important. So just substitute the limits. E equals k lambda into, this is negative, so you can substitute the lower limit. So lower limit is k lambda into, if you substitute the lower limit, x is equal to 0, it is 1 by z minus upper limit is 1 by L square plus z square whole power 1 by 2 in I cap direction, plus k lambda z into, just substitute the limits. What are the limits? It is, if you substitute the lower limit, it will be 0. So if you substitute the upper limit, it is L by z square into x square plus z square whole power 1 by 2. Whole power 1 by 2 in j cap direction. Clear? So if you just cancel this z, it will be k lambda by z. It will be k lambda by z also. So it will be easy. It is a k lambda by z. Okay. So that's it. So you got the electric field for a thin rod when the point is towards the end. So electric field is equal to k lambda into 1 by z minus 1 by z square plus L square whole power 1 by 2 I cap, plus k lambda by z into L by x square plus z square. So L square plus z square it could be. So L square plus z square If you substitute the upper limit, it will be L square. So it is a L square plus Z square whole power 1 by 2 in J cap direction. Is it clear? So this is the case when the point is towards the end of the rod. Okay, the first case we have found out the point is at the middle or it is symmetric, and here it has become asymmetric. Clear? Next, we discuss about this is the third case. We are discussing about an arbitrary point. An arbitrary point. See, this is an arbitrary point. It could be either at the middle. It could be either at the. It could be in the. It could be towards the end, or it could be anywhere. Okay, this is an arbitrary point, and it could, and you can apply this formula for any point for a thin rod. Is it okay? So, this is my thin rod. This is my thin rod, and this is where I consider my point. Okay, so this is my point. So this rod is of a length L, and I am considering the element here. This element contains a charge dq, and it is is of a width dx, which is at a distance x, and this point is at a distance z from the rod. Okay, so this is angle theta. This is angle theta. So you can if I place +1 coulomb here, it is repelled. So this is dE, and it could be resolved into 2. So this is a dE. This is a dEx. This is a x component, and this is a dEy, which is the y component. Okay, so this dEx, what is dEx? dEx is equal to dE sin theta. And what is dEy? Which is equal to dE cos theta. dE cos theta. That you know obviously. So, first I am taking this x component. I am taking this x component. So, what is dEx? dEx is equal to dE sin theta. dEx is equal to dE sin theta. So, what is this dE sin theta? What is dE then? dE is k 1 by 4 pi epsilon 0 dq divided by this distance x square plus z square into what is that? Sin theta. What is sin theta? Sin theta is x by under root x square plus z square, isn't it? So I got dx as kx and kx dq. I can also substitute for dq. dq is lambda dx. dq is equal to lambda dx. We already have discussed about that. So since I am substituting it here, dq is a lambda dx. It is a lambda into x dx divided by x square plus z square whole power 3 by 2. That is dEx. dEx is equal to k lambda into x dx divided by x square plus z square whole power 3 by 2. And what is Ex? Ex is equal to integral dEx. Take out the constants, k lambda into integral x dx divided by x square plus z square whole power 3 by 2. Is it not? So, what is it? Ex is equal to k lambda into integral x dx divided by x square plus z square whole power 3 by 2. We don't know the limits because this point is not symmetric. It is not purely asymmetric. It is somewhere in between. So we don't know the limits. Okay. So we are not putting the limits. It is minus 1 by x square plus z square whole power 1 by 2. Is it clear? So I am just dividing this by z and I am just multiplying this by z. So it remains unchanged. So Ex is equal to k lambda by z into minus 1 by z by x square plus z square whole power 1 by 2. And I am rewriting it. Ex is equal to minus k lambda by z into z by x square plus z square whole power 1 by 2. What is this? Z by root of x square plus z square. Z by root of x square plus z square. It is cos theta, isn't it? So Ex is equal to minus k lambda by z into cos theta. Minus k lambda by z into cos theta. Is it clear? So what is this? What is cos theta? So if this is my rod, and I am putting my point somewhere here, and I am taking an element here. Somebody can take an element here also. Somebody can take this element here. Okay, no problem. So here I have a theta. So here also I have a theta, and here also someone will have a theta, isn't it? So I am making it as a theta 1. This theta will not be equal to this because both are not the same. So this one is theta 1 and this is theta 2, isn't it? And this theta 1, see, it is from here to here. So it is in clockwise direction. Theta 1 is measured in clockwise direction. So we take theta 1 as negative. And whereas for theta 2 is from here to here. So theta 2 is in anti-clockwise direction, and we take theta 2 as positive. So cos theta varies from minus theta 1 to theta 2. Is it clear? So we got Ex equals minus k lambda by z into upper limit cos theta 2 minus lower limit cos of minus theta 1 is cos theta 1 itself. So it is cos theta 1. If you take this negative inside, you got Ex is equal to k lambda by z into cos theta 1 minus cos theta 2. Cos theta 1 minus cos theta 2. So you got the x component of electric field Ex is equal to k lambda by z into cos theta 1 minus cos theta 2. This x component also has the name the parallel component. Why? Because this x component is parallel to the rod. This is also denoted as E parallel. E parallel is equal to k lambda by z into cos theta 1 minus cos theta 2. Clear? Similarly, if you take this y component dEy, what is dEy? dEy is dE cos theta. Just substitute for dE. This is k dq divided by x square plus z square into cos theta. Cos theta is z by root of x square plus z square. So this z by root of this means it is whole power 3 by 2, isn't it? So we got dEy as k dq z divided by x square plus z square whole power 3 by 2. Is it clear? So we need Ey. So in order to get Ey, we have to integrate this dEy. Then what is this substitute for dq? Just substitute for dq. dq is lambda dx. So k lambda z into dx divided by x square plus z square whole power 3 by 2. Is it clear? So Ey is equal to integral that much. So it is k lambda z integral dx by x square plus z square whole power 3 by 2. X square plus z square whole power 3 by 2. Clear? So, what is the value of this integral? This is equal to k lambda z into k into x by z square into x square plus z square whole power 1 by 2. Okay, so this z and z cancels, and I am writing like this: k lambda by z into x by x square plus z square whole power 1 by 2. What is x by root of x square plus z square? X by root of x square plus z square is nothing but sine theta. So Ey equals k lambda by z into sine theta. What is this? Sine theta also runs from minus theta 1 to theta 2. Clear? So Ey equals k lambda by z into put the upper limit, it is sine theta 2 minus what is sine of minus theta 1 is minus sine theta 1, minus into minus plus, it is sine theta 1. So you got Ey as k lambda by z into sine theta 1 minus sine theta 2. Sine theta 1 minus sine theta 2. Is it clear? So you got the value of Ex and Ey. Ey is perpendicular to this rod, so we call it as the perpendicular component of electric field. E perpendicular. Clear? So these are the general cases, and from these general cases we got our first and second case. So you can try this for an infinite rod, and you can choose the thetas accordingly, theta 1 and theta 2, and you can apply this for an infinite rod which is infinite at both ends. You can also apply this for an infinite rod which is infinite at one end and finite at one end and infinite at another end. And also you can use this general expression for a finite rod also. Okay, so you can check this, and you can refer to our classes so that you can get more clarity about the applications of these equations or these concepts. Okay, so I welcome you to the classes of a competitive cracker so that you can have a better understanding of this. This is only a glimpse of what we have given in our classes. Okay, so so you can refer to our classes to know more about our classes. You can contact in this number so that you can get more details about our classes. So our CSIR net physics contains studio recorded classes, and you will have extra live classes while we near exams. And of course we are following the more syllabus oriented classes. Okay, so you will have a special live sessions, and we will cover complete syllabus before exams, and you will be provided with the PDF notes, and I request you to rely more on the notes and to get more data, more added up data to that notes, so that the note will become a complete package for your exam preparation. And also you can learn through our app and website, and exams will be purely computer based, so that you will get more familiar with CBTs, computer based tests, before the exams. So also you will be helped for solving previous year question papers also. These are the specialities of our CSIR classes, and of course you can rely on us 24/7. You can have a doubt clearance help from us also. So I welcome you all to Competitive Cracker, and hope to see you all in our classes, and bye bye. Thank you.